At exactly 4 seconds, this video reaches the highlighted moment. Sample the video at 1 frame per second, and the model receives that moment as frame 4. Sample the same video at 2 frames per second, and it receives the same moment as frame 8. The moment did not move. Only the number of sampled frames changed. So frame number tells us where a frame sits in the sampled sequence. It does not tell us by itself how many seconds have passed. Qwen 2.5 VL accounts for the sampling rate, so its temporal positions represent elapsed time. Videos vary in sampling rate. Images have a similar source of variation, their width and height. Those two images have different widths and heights. If we resize both to the same square, a tall document is compressed until its small text becomes unreadable. A wide banner must be squeezed or padded. The input size is consistent, but useful detail is lost. Qwen 2 VL replaced this fixed size input with a variable number of visual tokens, and Qwen 2.5 VL keeps that design. After processing, each 28 by 28 pixel region produces one final visual token. So a 28 by 224 image produces 8 tokens. A 1260 by 700 image produces 1125, and a 1092 by 8204 document produces 11,427. The processor still rounds and limits the image dimensions to stay within its token budget, but it does not force every image to use the same number of tokens. A larger processed image produces more tokens, allowing it to retain more detail. That solves the fixed size input problem, but it creates the next one. Attention must now process sequences containing thousands of visual tokens. How can it do that without comparing every token with every other token in every layer? To see what all-to-all attention costs, take one 896 by 896 image. The vision transformer divides each side into 14 pixel patches. 896 divided by 14 is 64. So the image becomes a 64 by 64 grid containing 4096 patch tokens. With full attention, each of those 4096 tokens is compared with all 4096 tokens. That is 4096 squared, or 16,777,216 token pairs in one layer. Qwen 2.5 VL uses local window attention in most of its vision layers. Divide the patch grid into 8x8 windows, and each token is compared with only the 64 tokens in its own window. Now the count is 4096 times 64, or 262,144 pairs. That is 64 times fewer pairs in this local layer. It does not mean the complete model runs 64 times faster. 4 vision blocks, numbered 7, 15, 23, and 31, still use full attention. In those blocks, information can move between any two parts of the image. After visual encoding, each 2x2 group of patch tokens is merged into one. The 4096 patch tokens therefore become 1024 visual tokens before entering the language model. This reduces the computation while retaining the image detail. But the model must still distinguish one row from another, one column from another, and one moment in time from another. That requires position coordinates. Each visual token needs 3 position values: its row, its column, and its time. Qwen 2 VL encodes these values with multidimensional rotary position embedding, or MROP. Rotary encoding rotates pairs of values in each token's query and key vectors by an amount determined by position. When attention compares 2 tokens, the difference between their rotations represents their relative position. MROP assigns separate rotations to time, row, and column. For text, all 3 position values increase together. For a still image, time stays fixed while row and column locate each patch. For video, row and column locate a patch within a frame while time locates it within the video. Qwen 2.5 VL changes how that time value advances. It sets the value from how many seconds have passed, not simply from how many frame groups the model has processed. Apply this to the 4-second video. The vision encoder groups 2 sampled frames into each temporal patch. At 1 sampled frame per second, each patch spans 2 seconds. The time IDs are 0, 4, and 8. At 2 sampled frames per second, each patch spans 1 second. The IDs are 0, 2, 4, 6, and 8. In both cases, 4 elapsed seconds receives time ID 8. The scale uses 2 position units per second. Faster sampling creates more temporal patches, so the time ID advances by a smaller amount per patch. Slower sampling creates fewer patches, so it advances by a larger amount. The time coordinate remains aligned with elapsed seconds instead of the number of sampled frames. These coordinates tell the model where and when each token came from. They do not teach it what information to extract from a document, which event to locate in a video, or which interface element to select. That comes from training. The training data makes those required outputs explicit. Given a document image, the model is trained to produce structured HTML that preserves its text, tables, formulas, and reading order. For repeated objects, it is trained to mark 1 point on each object before returning the count. For a video question, it produces the start and end times of the relevant event. For a screenshot, it identifies the requested interface element and returns the action to perform. Qwen 2.5 VL was pre-trained on 4.1 trillion tokens in 3 stages, 1.5 trillion for visual pre-training, 2 trillion for multimodal pre-training, and 0.6 trillion for long context pre-training. Qwen 2 VL used 1.2 trillion pre-training tokens. The video data used different sampled frame rates. This gives the model examples in which the same amount of elapsed time can span different numbers of frames. After pre-training, roughly 2 million supervised examples teach the model to follow instructions. Preference optimization then trains it to favor better responses over weaker ones. The vision encoder remains frozen during this post-training. This gives us a specific prediction. If these training choices worked, the model should perform well on document structure, grounded counting, locating events in time, and selecting elements and interfaces. The benchmark results let us check that prediction. The reported benchmark values let us test that prediction. For Qwen 2.5 VL with 72 billion parameters, DocVQA, which tests questions about document images, is 96.4. Count bench with detect, then count is 93.6. Charade's STA, which tests locating the start and end of a video event, is 50.9. The same table reports 35.7 for GPT-4o. ScreenSpot Pro, which tests locating controls in professional interfaces, is 43.6. The table reports 23.6 for Ogilvys 72B. These results are consistent with the outputs emphasized during training, but they do not show an improvement on every benchmark. On video MME without subtitles, Qwen 2.5 VL scores 73.3, below Gemini 1.5 Pro at 75.0. On OS World, which tests complete computer use tasks, it scores 8.83 below Ogilvys 72B at 10.26 and Claude at 14.90. On Hallusion Bench, it scores 55.2 below Qwen 2VL at 58.1. Video performance also depends on which frames enter the model. Evaluation can limit a video to 768 sampled frames. If those frames are sampled uniformly from a 1-hour video, then 3,600 seconds divided by 768 is about 4.69 seconds between sampled frames. A shorter event could occur between 2 samples and never enter the model. Elapsed time positions cannot recover visual information that was not included in the input. Finally, these results do not isolate the cause of any improvement. Qwen 2.5 VL changed the vision architecture, the language model, the amount and construction of training data, supervised fine-tuning, and preference optimization. The report does not provide controlled comparisons in which only one of those changes varies. So we cannot measure how much of a gain comes from elapsed time positions, window attention, or additional data. The benchmark tables report the performance of the complete model. They also show its limits. They do not measure the contribution of each individual change. Here's the precise comparison. Qwen 2VL already used variable numbers of visual tokens and separate coordinates for time, row, and column. Qwen 2.5 VL keeps both. Its new vision encoder uses local window attention in most blocks and full attention in 4. It also scales video positions by the sampling rate. so the same elapsed moment receives the same time coordinate. Training grows from 1.2 trillion to 4.1 trillion tokens, with explicit outputs for documents, counting, event timing, and interface actions. Several reported results improve, but not every benchmark does. And because the architecture, language model, and training all change together, the report cannot assign the gains to one change. So the precise takeaway is this: Qwen 2.5 VL processes detailed images more efficiently and represents video position using elapsed time rather than frame count.